So here we talk about several example ideas for our final project in this course. One of the idea is about deep learning and recommender system. Remember that previously we talked about a specific method called collaborative deep learning, where we combine a content-based method and collaborative filtering-based method, and also later vector models actually, in order to significantly improve the performance of recommender systems and basically address both the cold start item problem and cold start user problem, right? But in that specific method, we actually only talk about how to handle text-based content, basically items that can be represented by text. But one extension we can do is that what if the items can only be represented using images? For example, in Amazon, you may have a lot of items that can be represented by the images of this item. And in this case, you may need to have a new version of the collaborative deep learning or CDL model that can handle these images. And you might need to use some deep learning models such as ResNet, LensNet, or UseNet to extract features from these images. And you can either use the pre-trained model directly, or you can use the pre-trained model first, and then can fine-tune the model specifically for this recommender system model. This is one of the ideas. Another idea is that we can remember that in the CDL model and its recurrent version, we actually only use some very simple deep learning model like multi-layer perceptrons or recurrent neural nets. And recent advances in natural language processing, actually, they have proposed a lot of much more powerful models like Transformers, BERT, GPT-2, GPT-3, and these can all be used to further improve the performance. And let's say that again, in Amazon, we have a lot of items or products, and if we're given only the description of the product, can we improve the performance of the recommender system using these state-of-the-art NLP models like BERT and Transformer, etc., etc. And this is another idea. And the third idea is that what if the items that we want to recommend is not text, not images, but it's just a graph. And the graph is a very special structure. Basically, it's a set of nodes with connected edges. And examples of these may, for example, it may include a system that is asked to recommend a set of papers that cite each other, or the system may be asked to recommend molecule structures to synthesize a specific drug. And this molecule structure is actually a graph, right? So how do we modify or extend this CDL model such that we can actually recommend graphs? This is another possible idea. And the second general idea is about domain adaptation. For those of you who are not very familiar with domain adaptation, here is a 1-minute brief introduction. Basically, in a very traditional setting, machine learning, basically, we're given an X and we're trying to train a model to predict a Y, right? But in a domain adaptation setting, actually, we have two domains. Basically, we have a source domain, which is a data set, and we have a target domain, which is another data set. And usually, we are given the X and Y in the source domain, and we're given only the X in the target domain. And we want to train a model such that it can perform, we know that it can perform well on the source domain. So basically, it can predict the Y-axis very accurately, but also want to be somehow sure that the model, if we use the model to directly predict the YT in the target domain, it can also perform pretty well. So this is the setting for domain adaptation. And one thing we can do is that we can think about applying domain adaptation to recommender system. And one of the ideas is to think about cross-domain recommender system, right? And this is, for example, in this data set, they provide recommendation data set in about 20 domains. And let's say that we train the model in some of the domains, and can we use the same model and expect it to perform well in some other domain? So this is the problem of cross-domain recommendation. And another idea is to improve the domain adaptation itself. But this is more like a general machine learning problem. And here we provide a list of several state-of-the-art domain adaptation methods. Possible extension may be one. You can apply these methods to new data set, or you can apply these methods to new problems, or even more interesting, you can try to improve the methods themselves. And then yet another idea, the third general idea, is actually related to what we talked about dimensionality reduction. Remember previously we introduced a simple model to perform to perform dimensionality reduction. And the model is called stacked denoising autoencoder. So basically, stacked denoising autoencoder will use some corrupted version of the input data as input to the neural network, and it will go through several layers of neural network to recover the clean input, right? And this stacked denoising autoencoder, or SDAE, will use the middle layer, the output of the middle layer, as the representation for the data. And this is a low dimensional data. Therefore, it's basically dimensionality reduction. And we say that what if we have additional constraint or additional information about these items? For example, let's say that we want to do dimensionality reduction for a paper while taking into account the citation network. So basically, we have the text information about each paper, and we also have the citation links among this paper, and we want to perform this dimensionality reduction while considering this citation network. So this is one of the things that we have talked about previously in the lectures. So one idea is to extend this work by considering more complex graph. For example, in movie domain, we have actors, we have movies, and we have directors, right? And all these different nodes actually can be connected to each other. So basically, these are a very, very complex graph. We call it a heterogeneous graph, that we have different types of nodes, and corresponding to these different kinds of nodes, we also have different kinds of edges. And one problem is how to perform dimensionality reduction in presence of these kind of heterogeneous graphs. And the fourth general idea is about both deep learning and hashing. Remember, in one of the previous lectures, specifically when we talked about locality sensitive hashing, in one of the steps, we actually talk about how to use some general hashing algorithm to hash some strings into some bucket, and then we count the occurrences of such buckets, right? And one extension of these using deep learning is that when we're trying to count some kind of object, we can actually have a machine learning model, for example, a deep learning model in between, and we can classify in advance whether or not this is a heavy hitter or not. If it's a heavy hitter, then it's going to disturb the whole bucket. Therefore, it's best that we can assign a unique bucket to this specific object, right? And if we predict that it's not a heavy hitter, then we will resort to the normal hashing algorithm. And this is one way of incorporating or combining hashing algorithms and deep learning. Now, one idea of extending this is that we can consider whether or not to improve these machine learning models. For example, in this original paper, they only consider using a very specific and very simple neural network to classify whether or not this is habitable. Can we incorporate additional information or have a more advanced machine learning model to do this? And another idea is that whether we can replace this traditional hashing algorithm with some really machine learning based or deep learning based hashing algorithm. Now, this is another idea that we can think about. And the fifth general idea is to go from link prediction, go from link analysis to link prediction. Remember, in one of the lectures, we have talked about how to perform link analysis, basically how to determine the popularity or importance of each node in a web using the hyperlinks among these nodes. So this is called link analysis. And besides this, we can actually consider another problem, what we call link prediction. And link prediction is kind of one of the inverse problem where we're given two nodes and we have the content of the nodes and we want to predict whether or not the link between these two nodes exists. The examples of the applications of this kind of link prediction problem include suggesting Facebook friends. So Facebook is actually a graph, right? And we want to predict whether or not the link between two users exists. So that basically reduces to suggesting Facebook friends. Another application may be to suggesting references for scientific articles. So extensions of this may be, for example, we can think about how to use new methods. For example, you can consider using some state-of-the-art variants of GCN, graph convolutional neural net, to perform this task. Or you can think about applying existing models to new data sets like Facebook and Twitter data set. Basically, in Facebook, you will want to predict the links between the users, and in Twitter, basically, it's kind of like to predict whether or not some user will retweet some tweets, or some user will add somebody. And in terms of data set, we have several suggestions. For example, we can use site ULI A or site ULI T, and these two data sets are kind of like a content-rich data set because it contains both the recommendation part of the data set and also contains the graph structure of the data set. And we can also consider using this large pool of data set provided by the SNAP project in Stanford. Basically, they provide a very large pool of network data set that we can use. And besides all these five general ideas, we can also use and consider any other ideas and self-post the project. And as long as these ideas are related to the syllabus in this course, or it's related to any one of the topics in this GitHub repo.